Alright, my dears. So whenever I write a new lesson, I usually sit down and practice it, just to make sure it makes sense. I don't normally record myself, but I thought it might be helpful for you to have a recording of this, because this lesson is pretty involved. So here's what I'd like from you. By the end of this lesson, I should be able to give you reactants, and you should be able to tell me what kind of reaction is going to happen, what products is it going to make, what are going to be the structures of those reactants and products, balance that chemical reaction so that you can tell me what kinds of bonds are involved, how many of each, how much energy is in each bond, how much energy will be absorbed when the reaction happens, how much energy will be released, and finally, overall, is energy released or absorbed. And that's because I want to know, if I mix these two chemicals together, is heat going to come out, or is it going to absorb heat and get colder? Okay, and so that's going to be your answer at the bottom. So you have actually done all of these things with me in class at least once, but today I thought we would walk through it bit by bit so you know what's going on. So this started out with our question, or our example on page 80. And we started out saying, what would happen if we mixed hydrogen and oxygen together? Pure hydrogen gas and pure oxygen gas. So the first thing we asked was, what's going to be the reaction equation? We've already got it here, but let's walk through this one more time. Actually, you know what? I'm going to pause. On page 82, you're going to have another fuel, gasoline. Okay, I'm going to tell you right away, gasoline is made up mostly of octane. And octane, the oct means 8, C8, let me do some math in my head, H18, that's octane. And if it's a combustion, I already told you it's a combustion reaction. Well, let's say I didn't tell you that and I just told you I'm mixing it with oxygen gas. Okay. Alright, so you've already done this. We did this with hydrogen. Okay. So, when I told you I had hydrogen and oxygen, I told you I've got hydrogen gas plus oxygen gas, and what's it going to make? Well, we have learned how to do this, how to identify the category of a reaction, and that's what this page is for. This page is going to be on 83 in your notebook, but I'm not gluing these in because that'll make this recording a lot harder to follow. So if I just give you two reactants, you can absolutely figure out what's going to be created as a result. And we've got this in our notebook earlier. Let's take a look and see. Where did we learn about chemical reactions? We learned about them on page 9. So here we go. Page 9, and I'm going to add that to my page 83. Page 9 is going to be helpful here. Okay. So let's take a look. Hydrogen and oxygen. All right. Well, we actually already showed this as a synthesis reaction. You could think about it as a combustion reaction. It's just one without any carbon, so we're not going to make any carbon dioxide. But if you take a look, obviously that was the example, but this looks a lot like a synthesis reaction, adding two things together, because there's only one element in each of these reactants. Could it be a double replacement? Maybe, but that would leave us making OH plus OH, and since those are the same thing, it would leave us making 2OH. Is OH actually a thing that would happen in real life? Well, that's where you need to be able to predict the products, and you're going to do this based on what you know about electronegativity and ionic and covalent bonding. Whoa, that was a long time ago. Alright, so let's see where that is. That was all the way back in Unit 1. Let's find ionic and covalent bonding here. Where was that? Ooh, we're getting closer. All right, here we go. There's ionic and covalent bonding, and here's electronegativity. So these are pages 24 through 27 are going to be helpful for this. All right, so let's try to predict some products. First, let's get our electronegativities. Hydrogens is 2.2. Oxygens, if we look on the table, 3.4. What's the difference then between hydrogen and oxygen? If we subtract these, okay, the difference in electronegativity is going to be 3.4 minus 2.2. Is that 1.2? Yeah, I think that's 1.2. All right, where does that fit in up here? Is it greater than 1.9? No. Is it between these two? Yes. Okay, so it's going to be a polar covalent bond. All right, so how do we know how to make covalent bonds? Great question, Messiah. We did a little bit of this already down here. So we make covalent bonds, we have to look at valence electrons. We know that hydrogen's got 1, and oxygen has, let's see, that's 6. 1, 2, 3, 4, 5, 6. But here's the thing, we only care about unpaired valence electrons. So here's our oxygen again. 1, 2, 3, 4, 5, 6. We can draw hydrogen right here. So because these both have an unpaired electron, we know that they're going to make a bond, but that actually leaves oxygen with 1 more unpaired electron. So what's more likely? Is it more likely that another oxygen is going to make another bond with another hydrogen, and they're both going to have unpaired electrons? No, that's really unstable. What's actually more likely than the 2OH scenario that we just drew is that there's going to be another hydrogen here with another electron, and they're going to make another bond. And that's water. That is a compound that makes sense. Okay, so you did a little bit of practice for that down here. So when we're predicting our products, if we mix these together, rather than 2OH, what we're betting we're going to get is H2O. So that's going to be predicting our products. All right, so let's go all the way back to Unit 2, where we were originally. We're going to do a lot of page flipping today. And let's think about our octane example. So in this one, we predicted the products, and we found out what kind of bonds are going to be broken. All right, for octane, what kind of bonds are going to be broken? Well, we don't really know yet. There's actually some steps we have to do in between to be able to figure that out before we can list the type of bonds present. So when we did this yesterday, we did a really simplified version, but today I'm going to take you through each of these individual steps. So let's predict our molecular structures for the combustion of gasoline. Well, predicting the products is pretty easy because we know that this is a combustion reaction. So combustion reactions always make two things. They always make CO2 and they always make H2O. If you go back to page, why does that say 9? That's not right. Page 9. Oh, I wrote page 9 there. These reactions are on page 74. See, this is why I do this ahead of time. It's on 74. Or where I got 9 from. You probably know because you noticed it when it happened. So, we know we're going to make these two things. Now let's take a quick look. We've got carbon and carbon, hydrogen, hydrogen, oxygen, oxygen. Okay, that's good. We don't have anything over here that isn't still over here. And that matters because we cannot destroy matter. And we're also not changing one element into another. We might change one molecule into another, but we don't change one element into another. So let's predict our molecular structures. Well, honestly, CO2 and H2O are pretty easy, but humor me here, all right? And let's predict these structures. Okay. So this is, once again, you're going to use pages 24 to 27 to do this. So let's predict some structures. We've got carbon dioxide, all right? And the way we knew this was going to happen was we knew we were going to have carbon and oxygen. Okay, so here's our carbon and our oxygens. Okay, whatever they draw first is usually the central atom. I say usually because we're going to see something that is not true in just a second, but usually that's our central atom. And then we've got two oxygens, so I'm going to draw an oxygen here and an oxygen here. I don't really know where they're going to go, but we'll start with that. And there's a couple different ways I can do this. I can do the way that I just showed you previously, but I can also just count up all of my valence electrons. So if you go back to page 27, you'll see that carbon has 4 valence electrons, and oxygen, each of them, has 6, plus 2 oxygen atoms times 6 valence electrons each. That's going to give us a total of, let's see, 2 times 6 is 12, 13, 14, 15, 16. That's going to be 16 electrons. Okay, so here's how this works. We're actually going to make a bond for every 2 electrons, because each bond is electrons in a pair. So 16 electrons means we're going to make 8 bonds, or have 8 pairs of electrons here. All right, so let's start out just by putting the bonds that we know have to be there. We know oxygen and carbon have to be bonded together. All right, so that takes care of 2 4 electrons. Okay, well, what else can we do with these? Well, we know carbon usually has 4 bonds. Okay, let's give it each another bond there. So now carbon's got 2, 4, 6, 8 electrons around it. That's good. Oxygen has 2 4 around it. That's not as good. So we could add another bond, but the problem with that is now carbon will have, if we add another bond, it'll have 10 electrons around it. And we know that in that second shell of electrons around the atom, the max is 8 in that second shell. Where is that? Oh my gosh. That was way, way back. Let's see. Here we go. Oh my goodness. That was on page 15. Yeah, I think that's all the way back here on page 15. So, page 15 is also going to be helpful. Alright, so we can't do more than 8. That means we might just have some electron pairs left over, and that's okay. So that's one way to do it. The other way is the way I just showed you with hydrogen and oxygen. Instead of counting up the electrons and then putting out the bonds, and if we check, let's see, 1, 2, 3, 4, 4 lone electrons, well they're in pairs, but 4, we call these lone pairs, they're not involved in bonds. 1, 2, 3, 4, plus 5, 6, 7, 8 around oxygen. We know we've already got 8 around carbon, and this is the same, so we're all set. Alright, the next product is H2O. We just did that one. The way you can do that is do hydrogen, oxygen, hydrogen. We know hydrogen only makes 1 bond, right, because it's only got that 1 valence electron. We could just draw valence electrons and then draw lines to connect them. That's how we've done it previously. If you prefer that way, that's totally fine. You just have to check at the end. Does hydrogen have 2 valence electrons around it? Yes. 1, 2 in this bond. Does this one? Yes. 1, 2 in this bond. And does oxygen have 8? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Good. So these are our products. All right? Those are the products that we're predicting, those molecular structures. But wait. What about O2 and C8H18? We also need to know those because we're going to need to know what kind of bonds are being broken as well. All right, well, let's start with the easy one. Let's start with O2. Okay, O2 is going to be 2 oxygens. We know they've got 1, 2, 3, 4, 5, 6 valence electrons. Okay, well, this one's alone, this one's alone, this one's alone, this one's alone. We can just draw some lines right in between those. Does that one have 8? Yes. Does this one have 8? Yes. Okay, so O2 is pretty simple. Yikes, what about this one? All right, well, great question. C8H18. This is a pretty simple one. We've only got 2 kinds of atoms going on here. In general, carbon atoms tend to make chains. We also know that hydrogen atoms can only form 1 bond, which means they can only ever be on the outside of a molecule. So let's do this. Let me draw you a carbon chain. Let's just assume we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons in a chain. That's usually a pretty fair bet. Carbon tends to form bonds easily with other carbons. And let's say they each form a bond with one another. So there's, I'm going to stick with black for this. 1, 2, 3, 4, 5, 6, 7 bonds. Okay. So this carbon has 1 bond. That means 2 electrons in its outer shell. This carbon has 2 bonds, 1 on each side, which means 4 electrons. But these guys need more. Well, that's where the hydrogens come in. We have 18 hydrogens, so let's see how many that's going to be. If we put 1 hydrogen above and below each carbon, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, Okay, and we know that each of those has one lonely little electron, which can form one bond. So let's draw bonds in between here. Wow, I drew this kind of small. I'll do this differently in class. See, this is why I do this ahead of time. All right. Does every hydrogen have one bond? Yes. Does every carbon have 4 bonds? These interior ones do, but these ones on the end don't. The good news is we've only used up 16 of our 18 hydrogens, so probably what's going to happen here is we've got another hydrogen on each end. Okay, each of those hydrogens needs to have one bond. There we go. Now all of our carbons have 4 bonds and all of our hydrogens have 2. So that is probably our structure for octane. And if you look it up, you'll find that that's actually the correct structure. Excellent. So now we know what kind of bonds are going to be broken. Let's fill this in real quick. We know we're going to break, on this one, we're going to break carbon to hydrogen bonds, single bonds. We also know we're going to break carbon to carbon bonds, and again, those are single bonds. We also know we're going to have to break the bonds in O2. What's that bond? Well, it's an oxygen to oxygen double bond. Oxygen, oxygen double bond. Okay. Are we breaking any more bonds? No, that takes care of all of our reactants. All right. How many of each are broken? Can't answer that yet. We could count them up for one molecule, but do you notice we've got 8 carbon over here, but only 1 over here? It's because this reaction is not yet balanced. So we actually can't figure out how many of each bond is broken yet. So let me show you how to balance a reaction. All right, so we're going to rewrite our reaction right here. Okay, C8H18 plus O2 yields CO2 plus H2O. There's a couple ways you can balance, and you might get good enough at it that you don't have to take care of every single step, but here's how I like to do it. I like to draw a line down the middle to separate my reactants and my products, and I like to list my elements on the reactant side. I've got carbon, hydrogen, and oxygen, and on the product side, carbon, hydrogen, and oxygen, and I like to count them up. How many carbons do I have on this side? Well, that's 8. Do I see any more carbons? No. How many hydrogen? 18. How many oxygen? 2. How about on this side? Well, on this side I only see 1 carbon. I see 2 hydrogens, and I see 1 oxygen over here plus 2 over here. That's 3. Yikes. Odd numbers tend to make this complicated, but let's try it and see what happens. So what we're going to do, and this is the same thing we did with our water example, or our, where'd it go? Our hydrogen and oxygen example earlier. I showed you this and I said, all right, we've got 2 hydrogens over here, 2 oxygens over here, but when I write this, I see my 2 hydrogens again, but only 1 oxygen. Oh no, there go my papers. So what are we going to do? Well, we need 2 oxygens on this side. We can say there's 2 molecules of water. So now I've got 2 and 2, but wait, now I have 4 hydrogens. No problem. I can say we also had 2 molecules of hydrogen gas. And what I essentially did was the same thing that I'm about to show you, but because the next reaction is a little bit more complicated, we're going to actually count these up. So let me show you how this works. All right, so first I like to pick something that's only in 1 molecule on each side, and that's carbon. So I see I've got 8 carbon on this side and 1 carbon on this side. That's pretty easy to fix. I can put an 8 right here, which says now I have 8 carbons on this side. But wait, that changed something else too. How many oxygen do I have now? 8 times 2 is 10 oxygen here, plus the 1 over there. That's 11 oxygen. We don't love odd numbers in this. Okay, that's fine. Carbon's balanced. Why don't we do hydrogen next? Okay. Let's do hydrogen next. We've got 18 over here, 2 over here. So, how do we do that? Well, we can put a 9 here. Now we've got 18 hydrogen. It also changed our oxygen number again, though. We've got 10 oxygen over here because, wait, is that a lie? Oh gosh, I messed that up earlier, didn't I? See, this is why we do this ahead of time. 8 times 2 is 16, plus 1 more. Should have been 17. But now that I've got the 9 here, That's 16 plus 9 is 25. Oxygen. All right, well, there's nothing I can put out here that times 2 is going to be 25. Here's a trick that we do sometimes to fix this. You can multiply every single thing here by 2. So 2 of these means we now have 16 carbons, and we now have 2 times 18, 36 hydrogen. And a 2 here means we now have 4 oxygen. And this turns into 16, which means we now have, wait, did I do that right? 16, so we now have 16 carbon. And over here, 16 times 2 is 32 oxygen, plus I'm going to multiply this by 2. It's 18. So we've got 18 times 2 is 36 hydrogen. Now the oxygen's tricky. Let's see, that's 16 times 2 is 32, plus 18. What's 32 plus 18? Don't laugh at me for doing this the slow way. 2 plus 8 is 0, carry the 1, 40. Okay, 40. All right, my dears. So whenever I write a new lesson, I usually sit down and practice it, just to make sure. 40 oxygen on the side. Everything else is balanced. We got 16 carbons, 36 hydrogens, 40 and 4. Okay, no problem. We just need 40 oxygens over here. That's pretty easy. Instead of 2, this becomes 20. 20 times 2, that's 40. And once you have, all right, my dears. So whenever I write a new lesson, I usually sit down and practice it, just to make sure it makes sense. The same amount on both sides. For all of these atoms, you're balanced. All right, so let's write our final reaction here. Our final reaction is 2 atoms of C8H18. That's octane, which is gasoline, plus oxygen. How much oxygen? Well, it's going to take 20 molecules of that. I think I said atoms earlier. That's 2 molecules of octane, 20 molecules of oxygen, and those are going to react to form CO2 plus H2O, and we decided it was 16 CO2 and 18 H2O. All right, that's balanced. Whew, that was a lot. So let's add that to our reaction above. It's going to be 2, 20, 16, and 18. All right, good news. Now we have enough information to figure out how many bonds of each are going to be broken. All right. Wow, this is going to be fun. Here we go. All right, we've got 2 octane molecules. So in each octane, how many carbon to hydrogen bonds do we have? We have 18 of them, times 2, so that's going to be 2 molecules times each of them has 18 carbon to hydrogen bonds. How about carbon to carbon bonds? Well, let's take a look. There's one here, there's one here, here, here. That's 1, 2, 3, 4, 5, 6, 7. Okay, so we know that there's 7 in each molecule. And how many molecules of octane do we have? We have 2 of them, so that's 2 times 7. How about oxygen? Well, we know we've got 1 in each molecule, 1 bond, oxygen to oxygen double bond to break. And if I didn't make it clear, I'm writing this right below, because this is how many of these we have, this is how many of these we have. For this one, we've got 20 molecules of it. Whew. All right. What is the bond energy for each type of bond broken? All right. This is where we're going to have to check our chart. And the good news is, let's see, it says list type, let's look at our list. List types of bond present in the reactants. Ooh, and in the products. Okay. So let's actually do that part first before we figure out bond energy. Over here, it's asking us what bonds are formed. So let's look at what we actually make. CO2 and H2O. CO2 and H2O looks like in CO2 we have a carbon to oxygen double bond. Okay, and I'm sort of writing it right below so you can see it. Carbon to oxygen double bond. And in water, what kind of bond do we have? Pretty simple. We only have an oxygen to hydrogen single bond. Now, this might be a good time to pause the video and see if you can figure out how many of these we have, each on their own. Well, in each molecule of carbon dioxide, we have 2 of those carbon to oxygen bonds. And in each molecule of water, we have 2 of those oxygen to hydrogen bonds. But we know that we have way more than 1 molecule each. We actually have 16 of the CO2 molecules and 18 of the water molecules. Okay, so now we know we have listed the types of bonds present, and we've counted the number of each type of bond. So next, bond energy. All right, this is why I didn't glue it in, because this is going to be easier if I can flip my page. All right, we got to look up bond energies for each of these, and you should have this on page 81. And if you're keeping track of where each of these things is in the notebook, balancing the chemical reaction, I just showed you how to do that here. And if you open up this page, this should be glued on 83. I've got something to help you draw molecular structures and balance chemical reactions on the inside. So you can also look at 83 for this, and you can also look at 83 for this. How about where should you go to learn how to list the types of bonds present? Well, you've got that on page 80, you've got it on 83. I think 83 is the most helpful. 83 is the most helpful. But bond energy, that's going to be on page 81. Okay, so here's our bond energies. Let's see, for all of these different ones, we're going to find our bond energies. So, carbon to hydrogen. Let's look here. Do we see carbon to Yep, right here. Carbon to hydrogen. 413, and that's in kilojoules per mole. We haven't learned moles yet. I'm rethinking that. Maybe next year I want to do that differently, but for this year, I'll teach it to you later. It basically means how many of these molecules do we have. So carbon hydrogen, what's the bond energy for this one? 413 kilojoules, which is a measure of energy per mole. How about carbon to carbon? Well, that's right here. That's 347 kilojoules per mole. This is getting a little squished. This is another reason I do this ahead of time, so I can figure out where everything goes on the page. And oxygen double bonded to oxygen. Well, that's a multiple bond, so we're going to look down here. Here it is. This O2 is oxygen double bonded to oxygen. And actually, oh yeah, there we go. 498. 400. Wait, am I writing this in the wrong place? Oh my gosh, when I wrote these, I wrote them on the wrong line, didn't I? This whole bit is supposed to be here. This whole bit is supposed to be here. Did you catch that? That's why it's getting so squished. All right, no worries. Oxygen, that's 498 kilojoules per mole. All right, now down here, carbon to oxygen bond. If we look up here, it's 745. However, they have a note that we know for carbon dioxide, it's specifically at 799. So for carbon and oxygen, it's 799 kilojoules per mole. How about oxygen to hydrogen? Where do we find that? Here we go, oxygen to hydrogen. 467, that's kind of a 6, kilojoules per mole. All right. So, we found the bond energy associated with each. Now we're calculating the absorbed energy in breaking the bonds and the energy released in forming the bonds. So, I haven't done this yet for your class, so let's calculate this over here and show you how we calculate this. Really don't overthink this. Energy absorbed comes from breaking bonds, which only happens on the reactant side, and energy released comes from forming bonds, which only happens on the product side. So let's think about this logically. We've got 2 times 1 of this bond, and we know that every time we break it, it takes this much energy to break it. So let's think about this. We've got, for our hydrogen to hydrogen bonds, and we've got our oxygen double bond to oxygen. Those are the 2 bonds we're looking at here. We know we've got 2 molecules of that, and each molecule has one of those bonds, and to break those bonds requires 432 kilojoules per mole. Okay, we can do that math. That's pretty simple. My calculator. 2 times 1 times 432. 864. 864 kilojoules per mole. That's how much energy it takes to break apart that hydrogen gas. All right, how about the oxygen? Well, we've only got one molecule of it, and we're multiplying that by one oxygen to oxygen double bond. So this one's even simpler. One molecule of it times one bond in each molecule times 498 kilojoules per mole. Let's do that math. 1 times 498. Oops, no calculator required. 498 kilojoules per mole to break down the oxygen. Okay. How much total? Well, it's pretty simple. We can do this plus this, and that gives us a total number. And that is 864 plus 498. 1,362 kilojoules per mole will be absorbed as we break all the bonds on this side. All right, how much energy is going to be released? Well, let's take a look. On this side, we've got only one type of bond, hydrogen to oxygen, to think about. Hydrogen to oxygen. We've got 2 molecules of that, and each molecule has 2 of those hydrogen to oxygen bonds. And each one of those bonds takes 467 kilojoules per mole to break. So, if we do the math there, we could write it right here, but actually since there's only one of these, we don't need to write all of that twice. So 2 times 2 times 467. That is a total of 1,868 kilojoules per mole. That's energy released. All right. Whew. All right. So, if you wanted to see how to do this, page 80 will be very helpful for you. That's how we would do this for hydrogen and oxygen gas. But what about this one? Well, this one's a little bit more complicated. This would be a good time to pause this video and try this on your own if you haven't yet. But here we go. On the reactant side, we've got 3 types of bonds that we're breaking, and that's going to take energy. So here we go. We need to figure out for our carbon-hydrogen bonds, for our carbon-to-carbon bonds, and our oxygen double bond to oxygen. All right, so how much energy is going to be absorbed? Well, we've got 2 molecules of it, times, each molecule has 18 bonds, times, each one of those 18 bonds requires 413 kilojoules per mole. All right, so let's just set these all up. How about carbon to carbon? Well, we've got 2 molecules of that, and each molecule has 7 carbon to carbon bonds, and each carbon to carbon bond takes 347 kilojoules per mole to break. But wait, there's more! Don't forget about our oxygen. We have to break the... Alright, my dears. So whenever I write a new lesson, I usually sit down and practice it, just to make these bonds too. We've got 20 oxygen molecules, oxygen gas, times 1 bond each, times 498 kilojoules per mole. All right, shall we do the math on all these? All right, here we go. 2 times 18 times 413. That is 14,868 kilojoules per mole. The next one, 2 times 7 times 347 is 4,858 kilojoules per mole. And finally, 20 times 1 times 498 is 9,960 kilojoules per mole. So, how much energy does it take to break all these bonds? How much will be absorbed? Great question. Let's add them all together. Let's add all these together. 9,960 plus 4,858 plus 14,868. What do we get for a total? I don't like the spacing on this page. I'll change that in class. 29,686 kilojoules per mole. Wow, that's a lot of energy that's going to be absorbed. Whew. All right, how much energy was released? Well, shall we? What kind of bonds do we need to make? Every time we make one, we release energy. Here's our 2 bonds. We've got a carbon to oxygen double bond, and we've got an oxygen to hydrogen single bond. All right, those are the 2 that I'm thinking about here. Well, we've got 16 molecules of carbon dioxide, and for each molecule, there are 2 bonds that are carbon double bonded to oxygen, and it's going to take 799 kilojoules per mole that much is going to be released when we form that. How about oxygen and hydrogen? 18 molecules times, whoa, hold on, color palette, goodness gracious. 18 molecules, and each molecule has 2 oxygen to hydrogen bonds. That's that water molecule. 467 kilojoules per mole is released each time we build one. All right, let's do the math here. 16 times 2 times 799. 25,568 kilojoules per mole will be released from that one. And as we form the water, 18 times 2 times 467. That's 16,812 kilojoules per mole. And when we add these all up, gosh, I hope I didn't make any errors in this. If I did, forgive me, and look at the online notebook. That will definitely have the right numbers for all this. 25,568 plus 16,812. So total 42,380 kilojoules per mole is going to be released as those bonds form. We're almost there, folks. Finally, we're going to estimate the net enthalpy of reaction. What is the enthalpy of the reaction? So glad you asked. Good news, you actually have notes about this, bond enthalpy. That is on page 78, and I think that will be helpful. If you have not done that yet, that should be your top priority. So, let's figure this out for our hydrogen example. We're back on page 80. So if this much energy is absorbed and this much is released, then overall, do we release energy, absorb it? Well, this number is bigger, so overall I think we're going to release energy. But don't forget that this much is being absorbed. So let's do this. 1,868 kilojoules per mole released. And let's subtract the energy that was absorbed. 1,362 kilojoules per mole absorbed. When we do that math, that's going to give us our net enthalpy of reaction, meaning what we gained minus what we lost. You'll hear that in economics as well. So 1,868 minus 1,362, that's 506 kilojoules per mole released through the combustion of hydrogen. And we can write that, or we can just write 2H2 plus O2 yields 2H2O. All right. Back to page 81, our final example. What do you think? Overall, did this reaction of gasoline, which is octane, absorb or release energy? Well, using our brains, we know that when we burn gas, it produces heat. So it shouldn't be surprising that more was released than was absorbed. But let's do the math anyway. So 42,380 kilojoules per mole released minus 29,686 kilojoules per mole absorbed. Okay, how much is going to be released total overall? Let's take a look. 42,380 minus 29,686, total of 12,694 kilojoules of energy released per mole from octane's combustion. I could just write the equation again, but I like to be thorough. All right, my dears, so that was the whole thing, and it was a lot, I understand, but we've got our octane example, and we've got a list of steps for you on how we got there. So now it's time to go back to this. Will this reaction be endothermic or exothermic? And if you want to learn more about endothermic and exothermic, check our notes pages. That's going to be back here on page 79. All right? But your job is to walk through this process for these two molecules all the way to the end and tell me, is it going to release energy or absorb energy? I do want to give you one little hint, because this is kind of a tricky molecule to figure out the structure. Let's take a close look. CO, oh goodness, I need to adjust. There we go. This is kind of a tricky one. Remember, they usually do the central molecule first, so we're probably going to have a carbon and an oxygen toward the center. And then NH2, and then in parentheses 2. That's telling us that we have 2 of this NH2. So it's probably going to be, whoops, I meant to write an N, H, H, we've got one of those, and another N, H, H. Why did I write it that way? Well, I've been doing this a long time. I know nitrogen can form many bonds, but hydrogen can only form one, so I usually write my hydrogens around the outside. And now, honestly, I'm just going to start making bonds. I know they've got to be here somewhere, and then counting up. All my hydrogens each have one bond, good. Nitrogen, how many does it have? Well, nitrogen has 1, 2, 3, 4, 5. That's its valence electrons. It's got 3 lone pairs, so probably we've got some extra valence electrons sitting here, but this one's happy. It's got its 8. Carbon, it needs 1 more, but no problem, because actually so does oxygen. All right, it's got its lone pair, so carbon's got its octet, oxygen's got its octet. Yep, there's your structure. So I just wanted to show you that one because it's a little unusual. Your job is to predict the products based on what type of reaction you think it's going to be, and then figure out endothermic or exothermic. Best of luck, folks. When you're all done, take your proposed answer and fold this up. You're going to write a hypothesis based on this, because we're actually going to test this hypothesis in class.